Hello, this is derivatives, one of the first units you learn in calculus. So what derivatives are basically an equation to find the instantaneous slope at any given point on a graph. So let's say we have the graph x squared. Well, we can find the slope of it at any given 2 points, such as 1, 1, and 2, 4. What you basically do is you find the change in y over the change in x.
But that is not the instantaneous rate of change. That is the average rate of change between the 2 points.
This is true because if you get on close to the graph, all it looks like is point, point.
Looks like a secant line.
It does look like a secant line.
And that's not what we want. We want a tangent line.
Yep. By the way, tangents look like that, if you didn't know. There's several ways to go about this. One of them is to get so close, zoomed in on the graph, that you can't help but estimate the tangent line.
Yeah, but that's a little bit hard to do sometimes if you're doing it by hand especially.
Yes. So
there's a way easier way to do it.
Instead we use this equation. F of x plus h minus f of x all over h as limit equals
h approaches 0. And the reason you can't just plug stuff in right here is because you can't plug 0 into the denominator.
Yes, it just
basic algebra, guys.
Nothing works there.
It's undefined.
So let's say we use this equation up here, x squared. Well, what that looks like is x plus h squared minus x squared all over h.
And we could show you how to multiply that out, but you should know that by now. So we're just going to skip right to it.
And you get your derivative, x squared, or 2x. I'm sorry.
What are you doing? No.
2x, right? Fun work. But
there's a way easier way to do it.
That's really long and boring. Not everyone has time to do that.
No, no one has time to do that.
So let's just look at these patterns here, though. So we know that x squared, the derivative of that, by the way, this is what derivative looks like. You'll have a little dash right there.
And you can do that for second derivatives and triple derivatives and stuff like that.
Second derivative. Ha ha ha. Oh, look at the third derivative. Yay!
But
whatever.
You don't use those right now.
No.
We're just doing the first derivative.
So for the first derivative of x squared equals 2x, which is something we just learned. The first derivative of x cubed equals 3x squared. And the first derivative of x to the fourth, 4x to the third, and then 5x to the fourth. Notice a pattern here, kids?
I sure don't. Why don't you tell me?
Wow. So the pattern is that if you see this exponent, it is always moved to the front, and somehow this exponent is always one less than right here. So the equation for that is n minus 1. And to use this, let's show an example of this.
Okay.
So for x to the fifth, we'll have x to the fifth minus 1, and we'll just move the 5 down here.
Hey.
We'll have 5x to the fourth.
Awesome.
Look, they are the same.
Well, no, yeah.
That one.
That one's the same. Yeah. Alright, that's your basic derivative rule stuff. But what if you have a coefficient already in front of the x?
That's a good question that has puzzled many of us for a long time. Instead, use this equation. So
let's do 2x to the fifth.